All right, I think I'm ready to take on the loop unrolling stuff. So I need to hit the lights here because I can't see shit. Loop unrolling. Loop unrolling is a program. I don't like that lighting. Loop unrolling is a program transformation that reduces the number of iterations for a loop by increasing the number of elements computed on each iteration. We saw an example of this with a function psum2, figure 5.1. Let's go back there. 5.1, I don't remember that. Figure 5.1. Here it is. Yeah, I remember that. Let me catch the last one at the end. Where each iteration computes two elements of the prefix sum, thereby having the total number of iterations required. Loop unrolling can improve performance two ways. First, it reduces the number of operations that do not contribute directly to a program result, such as loop indexing and conditional branching. Second, exposes ways in which we can further transform the code to reduce the number of operations in the critical path of the overall computation. In this section, we'll examine simple loop unrolling without any further transformations. Figure 5.16 shows a version of our combining code using what we will refer to as a 2x1 loop unrolling. The first loop steps through the array 2 elements at a time. That is, the loop index I is incremented by 2 on each iteration, and the combining operation is applied to array elements I and I plus 1 in a single iteration. In general, the vector length will not be a multiple of 2. We want our code to work correctly for arbitrary length vectors. We account for this requirement in two ways. First, we make sure the first loop does not overrun the array bounds. For vector length n, we set the loop limit to be n minus 1. We are then assured that the loop will only be executed when the loop index I satisfies I is less than n minus 1, and hence the maximum array index I plus 1 will satisfy I plus 1 is less than n minus 1 plus 1 is equal to n. We generalize this idea to unroll a loop by any factor k, yielding k times 1 loop unrolling. To do so, we set the upper limit to be n minus k plus 1, and within the loop apply combining operations to elements I through I plus k minus 1. Loop index I is incremented by k each iteration. The maximum array index I plus k minus 1 will be less than n. We include the second loop to step through the final few elements of the vector one at a time. The body of this loop will be executed between 0 and k minus 1 times. For k is equal to 2, we use a simple conditional statement. Makes sense? So optionally add a final iteration as we did the function psum2. For k is greater than 2, the finishing cases are better expressed with a loop. And so we adopt this programming convention for k equals 2 as well. We refer to this transformation as loop k times 1 loop unrolling, since we unroll by factor k but accumulate values in a single variable accumulator. Okay. So we combine 5. So we go by 2 and then we go by 1 at the end. Okay. Modify the code for combine 5. I'm not going to do that problem. So up to 5.7 we're skipping. So if we go ZZ here, 5.5, skip, 6, 7, skip. Okay. CPU performance for different degrees of k times 1 loop unrolling only gives integer addition improves with this transformation. God, it is so freaking hot in here. I'm gonna turn the AC on. Every day, man, it's like oscillating between extremely hot and extremely cold. Extremely hot, extremely cold. I really don't give a shit about loop and rolling. It's a pretty basic concept. Alright. Let's continue reading. CPE performance for different degrees of K times 1 loop unrolling. Only integer addition improves with this transformation. Only slightly. We see that CPE of integer addition improves, achieving the latency bound of 1. This result can be attributed to the benefits of reduced loop overhead operations. By reducing the number of overhead operations relative to the number of additions required to compute the vector sum, we can reach the point where the 1 cycle latency of integer addition becomes the performance limiting factor. On the other hand, none of the other cases improve. They are already at their latency bounds. Figure 517 shows CPE measurements when unrolling the loop by up to a factor of 10. We see that the trends we observe for unrolling by 2 and 3 continue. None go below their latency bounds. To understand why K times 1 unrolling can't improve performance beyond the latency bound, let us examine the machine level code for the inner loop of combined 5 having K is equal to 2. The following code gets generated when the type data T is double and the operation is multiplication. We can see that GC uses more direct translation of the array referencing we see in the C code compared to the pointer-based code generated for combined 4. GC Optimizer operates by generating multiple variants of a function and then choosing one that it predicts will yield the best performance in smallest code size. As a consequence, small changes in the source code can yield widely varied forms of machine code. We found that the choice of pointer-based array code has no impact on the performance of programs running on our reference machine. Okay, we can see that GC uses more direct translation of the array referencing seen in C code compared to the pointer-based code generated for the combined 4. Loop index I is held in register RDX, and the address of data is held in register REX. As before, the accumulated value ACC is held in vector register X0. The loop unrolling leads to 2 vmult SD instructions, one to add data I to the accumulator, and the second to add data I plus 1 to the accumulator. The figure 518 shows a graphical representation of this code. The vmult instructions each get translated into 2 operations, one to load an array element memory, one to multiply by its value, the accumulated value. So here the register XMM0 gets read and written twice in each iteration of loop. We can rearrange, simplify, and abstract this graph following the process shown in figure 519a to obtain the template shown in figure 519b. We then replicate this template n over 2 times to show the computation for a vector length n, obtaining the data flow representations. I don't really like his graphing stuff. Shown in figure 520. Here we see that there is still a critical path of n mult operations in this graph. There are half as many iterations, but each iteration has 2 multiplication operations in sequence. Since the critical path was a limiting factor for the performance of the code without loop unrolling, it remains so with K times 1 loop unrolling. Aside, get the compiler to unroll loops. I was going to say, compilers do loop unrolling. Loop unrolling can easily be performed by a compiler. Many compilers do this as part of their collection of optimization. GC will perform some form of loop unrolling when invoked with optimization level 3 or higher. Okay, that's loop unrolling. let's continue watching from here, see what his lecture is about.
Rather than executing one value within a loop, you execute multiple ones. And so this code shows unrolling by 2. And what it says is I'm going to step through this array 2 elements at a time. And within each of the inner loop, I'm going to combine the values from di and di plus 1. And I have to put in some extra code to finish off what happens if the original array was of odd length. But you get the idea. And this idea, I show this code of 2, but you could imagine this applying for different values of loop unrolling. So will this help us any? Well, when I run it, I get that the integer addition got a little faster, but the other ones didn't improve at all. So this one is going faster because basically the old code, just the overhead of the loop indexing and incrementing was enough to be slowing me down because it's already close to a clock cycle. So I just managed to knock that down to be at the latency bound of this particular instruction. But it didn't improve the other ones because I still have this sequential dependency. In order to get my new value of x, I have to first do one computation and then do the other before I can begin another one. But this shows me the way I could make a very, very small change and change performance fairly dramatically. What if I take these parentheses and shift them to the right? Would that make any difference? Shift them. Shows me the way I could make a very, very small change and change performance fairly dramatically. What if I take these parentheses and shift them to the right? Would that make any difference? And lo and behold, yes, you find that, and I'll call that transformation unrolling by 2, computing one element at a time. I'll talk about that in a minute. But I'll use this lowercase a to say I've done an associativity transformation. And you see, all of a sudden, my time's dropped in half for these 3 cases. So something's going on. And so let's see why that is, and now I'll introduce it. And so if I take my picture from before and think about what those computations imply, you'll see that right now I've changed the structure of the computation so that I'm pairwise combining each pair of elements of the array and then accumulating those into the overall computation. So I've actually, that shifting of the parentheses fundamentally changed how I'm doing my computation. And you can see now that this critical path, which is what determines, in this case, the performance limitation, just got shorter by a factor of 2. And that's why I'm now running twice as fast for the operations, not for integer addition, but for the other 3 operations I've cut by a factor of 2, just by that shift. Now there's some good news and bad news here. The good news is if this is integer arithmetic, we know already, you know that 2's complement arithmetic is associative and commutative. So it really doesn't matter for both multiplication and addition. So it really doesn't matter what order I combine these elements in. I'm going to get the exact same answer no matter what. But you also saw for floating point that's not the case. So with floating point, that shifting these parentheses, because of rounding possibilities and even potentially overflow, you might get different values, results from these computations. But then again, if you think about, is that really going to happen? Chances are no, that it's not really going to affect the outcome of your program. but it's enough of a change that most C compilers, or most compilers period, will not make any change that changes associativity, because they're very conservative when it comes to floating point. So that's something you as an application programmer has to know well enough. Is this a valid, can I do this transformation without messing things up? And now what I'll say is now there's a new set of bounds. So a bound is what would appear to be sort of the best you can do based on some constraint in the program. And before it was saying, well, the latency, the total time through for a given operation was a bound. And now I say, well, there's an even more fundamental bound, which I'll call the throughput bound, which is just based on I only have so much hardware out there, and I can only pump it so fast. So for example, these two, the throughput bound is 1 because I only have that actually becomes limited by the requirement that I'm having to read from memory, and I have 2 different load units. Oh no, I'm sorry. I only have 1 multiplier for integers and 1 for addition. The throughput bound for these 2 actually is just a half, because it turns out there's some odd part of the hardware design that has 2 floating point multipliers, but only 1 floating point adder. And we'll see that we can actually make this multiplication code run faster than addition code. And over here, again, my limit will be that I only have 2 load units, and I have to be and I have to read for every element I'm computing. I have to be reading 1 element from memory, so I can't get below that. Okay, so but we saw this some odd part of the hardware design that has 2 floating point multipliers, but only 1 floating point adder. And we'll see that we can actually make this multiplication code run faster than addition code. And over here, again, my limit will be that I only have 2 load units, and I have to be and I have to case it 1. Now you here would talk about that in a minute, but I'll use this lowercase a to say I've done an associativity transformation. And you see, all of a sudden, my we have 1 run fast. Information now has let us break out of this latency limitation and get something closer to throughput. Here's another technique that can be used to, again, sort of get more parallelism going. And I call this multiple accumulators. And the idea is, let's imagine that we have the odd numbered elements and the even numbered elements in the array. And we can compute separate sums or products of those 2 sets of elements, and then at the very end combine them together. So this is another form of an associativity transformation. We're changing the order in which we combine things together. It's just that we're doing it in this sort of odd-even manner, or in general, every ith value if we do it by some parameter I. And it has the same issues, that if it's integer arithmetic, it's fine. If it's floating point, there's a risk of changing the behavior of the program. But you'll see that, again, we get a cutting in half here and a little bit below 1 for integer addition. And again, we can think of it by looking at these pictures of what gets computed. And you see what we're doing is we're computing. Here are all the even numbered elements being combined, and here are all the odd ones, and then at the very end we're combining those together. And so we can generalize this. If we can unroll by a factor of k, of L, and we can accumulate k results in parallel, and we can use various values of L and k for it. In general, L has to be a multiple of k. And so you run it out, and you can get, for floating point multiply, you can actually get it down almost to this throughput bound of 0.5. This is incorrect. This is integer addition. That should say int addition. You can, again, get it down to around 0.5. And in general, by sort of picking the best parameters, I can get very close to the throughput bound of this processor. So I've been able to take something, remember, it originally was 20 clock cycles, then 10, and now I'm getting it down to 1 or fewer clock cycles per element. So now, just as
okay, so that was loop unrolling. He talked about multiple accumulators, which he's going to talk about again in the book here. So I did get a little bit ahead on the lecture. He talks about the reassociation, transformation. Goes over as a summary. Has 2 webasides for SIMD. Oh no, that's the same webaside. There's a webaside for SIMD. Which I don't think he talks about SIMD other than in the aside. Some limiting factors: register spilling, branch prediction, and misprediction penalties. Understanding memory performance, load and store performance, life in the real world performance improvement techniques, identifying and eliminating performance bottlenecks. Summary. Okay. So I got a little bit ahead on the lecture. I thought he didn't write about this stuff, but he did. Okay. Let's go over here. I do want to... How do I do these asides? Webaside down here. Yeah. So it's already here. And whether we're going to skip it or not, I don't know. I feel like SIMD stuff is something I want to do more of. So CSAPP, webasides, SIMD. And this is how many pages? Boom, boom, boom. 11 pages, not too much. Okay, so let's step through this. An introduction, declarations. So it's going to be a vector size attribute. These are just constants that we defined, which is v bytes and v size, or vector size, number of bytes. Okay. And we call that type of vector t. And we accept that. So this is going to be the attribute vector size. So we single step until we have memory alignment, and we step through data with V size weight parallelism, and then we single step through the remaining elements. And then you combine all of the elements of the accumulated vector into a single result and write that out to destination. And then we have a little analysis and 6 practice problems and some solutions. Okay. I think I'll do that one. Not tonight though. Okay, we're at enhancing parallelism with the accumulators. We've watched the lecture. I don't really want to go too further. In fact, I don't want to go any more further into this today. So just to kind of track my progress here, got from 572, so that's where we landed. I think we started at the 5, right? Did we start? Where did we start this morning? I think we started on chapter 5 this morning. Yeah, I remember starting at chapter 5 this morning. Okay, so that's 532. 532. It's about 50 pages. No, I'm trying to do math here. Thank you. 40 pages. Okay. Yeah, that makes sense. Okay. Let's go ahead and close up shop on this book today. It was fun, but I'm done. Alright, so we got all the way up to here. Oops. Rx dot 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 dot. Okay. Get status. We'll do get at all. Get status. Get DC. $572. This is a do whatever the hell I want stream, so I think I'm going to think about what I want to do here. The sun's setting, so I can move my desk back. That's nice. Maybe we'll like watch a talk or read another like little tiny blog post or something. Or we can read some more of the Learning Linux Binary Analysis book. Or we can do some Brilliant. I kind of feel like I should at least check in on Brilliant because I don't think I have done anything today. Oh no, I did something today. I'm just trying to keep my streak alive, but how am I still second? Oh, because I got 2 hours left. I don't give a shit about Brilliant today then. Guess it expires Sunday night. Wow, Sarah just knocked it out of the park this weekend. She started doing a bunch of stuff. Yeah. I don't know. I don't know what to do. I definitely don't want to continue reading on the computer systems book or reading the lectures. Because I feel like I'm pushing that a little too hard right now. And I'm just getting back into it, so I don't want to push it too hard. Alright, well, let's pick up the Learning Linux Binary Analysis book. And just do some reading on that. So where do we leave off here? Okay, we're doing readelf stuff. We learned about relocations, that's right. This shit is hard, man. Bunch of fucking memory addresses and confusing shit. And I kind of had enough C. I want to do something fun. This is less fun. This is more of the shit that I'm doing in the CSAPP book. It's looking at disassembly and learning about these low-level things, like reading C code that's fucking insane. I just don't feel hugely motivated to read this Linux binary analysis book right now. Which is a bummer because that's like my failover book for when I'm like really like tapped. I think I'm just too in the weeds on x86 assembly and low level shit right now. I could read like an easy book, like a Soul of a New Machine, or the Intel book, or the AI book that I bought. Like those are like super casual. Maybe I do that. I mean, this is a do whatever the fuck I want stream. Or I could get started on the systems design interview book. Let's leaf through that a little bit. So this is supposed to be the better one of the two. I got both of them. This is volume 2. It's supposed to be the better of the two. Apparently he had a co-author, San Lam, who apparently improved the content of the book. This book is fantastic. It is a great continuation of the first book. I strongly recommend it to anyone who's studying systems design interviews. Sunny Patel, software engineering manager at Microsoft. I was tech lead at Fang, but need help in getting up to speed with unfamiliar domains. If you put in the work, this book will help you acquire the breadth and depth of knowledge you need for talking about bottlenecks and alternatives as expected of a tech lead. Roberto Degano, staff software engineer at Coinbase. Hey, I was a staff engineer at Coinbase. I don't know this guy, Herbert Degano. When was this book published? 2022, okay. He would have been there when I was there. Herbert Degano. Coinbase. So he's at Amazon now. I don't remember him. What's inside? An insider's take on what interviews really look for and why. A 4-step framework for solving any systems design interview question. 13 real systems design interview questions with detailed solutions. 303 diagrams to visually explain how different systems work. Alex Zhu is a software engineer and author. His book, Systems Design Interview and Insider's Guide, Volume 1, is an Amazon bestseller, which has been translated into 6 languages. He's worked at Twitter, Apple, and Zynga. San Lam is a software engineer with decades of experience in building scalable systems at high-growth companies like Discord, Zynga, and NetApp. He has designed, built, operated, and optimized many interesting distributed systems used by millions of users. You can connect with Alex on social media, where he shares systems design interviews tips every week. Okay. Wonder if he's still keeping that up. What does this book smell like? That's an important test. It smells like chemicals. I don't like the smell of this book. Okay, so there's 13 problems, he said, 13 chapters, so each chapter is probably a problem. Proximity service, nearby friends, Google Maps, distributed message queue, metrics monitoring and alerting system, ad click event aggregation, hotel reservation system, distributed email service, S3 like object storage, real-time gaming leaderboard, payment system, digital wallet, stock exchange. The last one would be relevant for Coinbase. don't know if this is what I want to do though. What's odd is they don't really teach you about the system design interview, even though the fucking name of the book is Systems Design Interview. I mean, I've done a number of systems design interviews at different companies, and I've had to also go through systems design interviews at a number of companies. There's definitely like a formula that people recommend: gathering requirements, asking clarifying questions, like talking through possible approaches, and then diagramming out those approaches once the interview has like kind of confirmed that you should go down and start diagramming. I don't really know why, like, why would I want to solve this problem, proximity service? I feel my brain just being like not wanting to solve problems right now. Maybe I just need to like chill the fuck out and like do some easy ass brilliant stuff. I don't know. Last night I talked a lot about like perspective and my overall objectives, learning objectives. And that was like really, really good use of my time. But now I'm like looking around, or like there's plenty of things around me that I want to, in theory, read and learn about. But like I break this open and I look at the table of contents of like problems that they're solving, and it's just like, I mean, these would be interesting problems to work on, but it's just not something that, okay, proximity service, nearby friends, Google Maps. The only thing that interests me here is chapter 4, distributed message queue, that kind of, because that's like a primitive that you can use to build larger systems. That seems like something that would be interesting to me. Metrics monitoring alerting system. I mean, I built like so many of those already. It's just like, okay. Add click event aggregation. Don't care about that. Hotel reservation system. Don't care about that. Distributed email service. Maybe. S3 like object storage. Yeah, that would be interesting. Real-time gaming leaderboard. Okay. Not super interested in that. Payment system. Not really super interested. Digital wallet. That comes from Coinbase. Stock exchange. Another Coinbase one. It's like, none of these scream like, oh, that'd be so fucking cool to work on. Maybe it's just my current mood. It's getting late in the day, and maybe that's just where my motivation is at. Let's look through the volume 1. See if there's anything in there that is really interesting to me. Scaling. That is interesting. back of the envelope estimation is interesting. A framework for system design interviews. Design a rate limiter. Design consistent hashing. These are all interesting. These are more interesting to me than the volume 2, which is interesting that people recommend the volume 2 over volume 1. Design a key value store, design a unique ID generator in distributed systems, design a URL shortener, design a web crawler, design a notification systems. All these look way more interesting. That is fascinating. That I'm interested in the book that everyone said that is worse than the sequel. What am I feeling like? It's already 7. I just got 1 more hour left. Maybe let's read The Soul of a Note Machine. I've been wanting to read that for a while. This book smells a lot better than the chemical book. I think it'll be more fun. It says published, just for context, August of 81. Wow. This one was printed, seems to be 2000 maybe? Prologue. Good Man in a Storm. All the way to the horizon in the last light. Let me something I can point to here. All the way to the horizon in the last light, the sea was just degrees of gray, rolling and frothy on the surface. From the cockpit of a small white sloop, she was 35 feet long. The waves looked like hills coming up from behind, and most of the crew preferred not to glance at them. There were no other boats in sight, but off the south for a while they could see the reassuring outlines of the coast. Then it got dark, running under shortened sails in front of the northeaster. The boat rocked one way, gave a thump, and then it rolled to the other. The pots and pans in the galley clanked. A six-pack of beer, which someone had forgotten to stow away, slid back and forth across the cabin floor. Over and over again, sometime late at night, one of the crew raised a voice against the wind and asked, what are we trying to prove? All of them were adults. The owner and captain was a lawyer in his 60s. There were a psychologist and a physician and a professor, all of them in their late 30s. And also a man named Tom West. West was rather mysterious because the merest acquaintance to one of them and a stranger to the others. They were bound for New York from Portland, Maine. That's not that far. On yachtman's business, which is to say primarily for sport. And when they had set sail in sheltered Casco Bay earlier that evening, decked out bravely in slickers and sou'westers, all of them had felt at least a little bit romantic. But when they cleared the lee of the land and entered the seaway, and the boat suddenly began to lurch, they grabbed the nearest sturdy things and thought about their suppers, which by the time it got dark, several of them had lost. Most of the crew now fell into that half autistic state that the monotony of storms and seas occasionally induces. You find a place to sit and get a good hold of yourself. You try not to move again. The boat rolls this way and you flex the muscles around your stomach, then relax. She rolls that way and you flex again, just staying in one place is exercise. For a while your mind may rebel. Why did you come, idiot? I'm going to get a bookmark here because I'm having a hard time scanning these pages. Why'd you come, idiot? You don't have to be out here. You may feel remorse for having cursed some part of life on land. After a time, though, phrases started falling from your memory, snatches of songs or prayers or nursery rhymes, and you repeat them silently. A little shot of spray in the face, however, or an especially loud and dangerous sounding thump from the hull, usually breaks the trance and puts you back at sea again. You feel like a lonely child. The ocean doesn't care about you. It makes your boat feel tiny. The oceans aren't great promoters of religion, or at least of humility, but not in everyone. The oceans are great promoters of religion, or at least of humility, but not in everyone. In the glow of the running lights, most of the crew looked like refugees, huddled, wearing black faces. Among them, Tom West appeared as a thin figure under a watch cap. In nearly constant motion, high spirits had apparently possessed him from the moment they set sail, and the longer they were out in the storm, the heavier the weather got, the livelier he grew. You could see him grinning in the dark. West did all that Captain asked, so cheerfully, unquestionably, and fast, that one might have thought the ghost of an old-fashioned, virtuous seaman had joined them. Only West never confessed to a queasy stomach. When one of the others asked him if he felt seasick too, he replied in a completely serious voice that he would not let himself. A little later, he made his way down to the cabin, moving like a veteran conductor in a rocking, rolling railroad car, and got himself a beer. West was at the helm, the tiller in both hands, riding the waves. He was standing under a swaying lantern in the cabin, studying the chart. He was nimbly climbing out onto the foredeck to wrestle in a jib and replace it with a smaller one. And when the captain decided to make for shelter very late at night at a little harbor with a passage into it that was twisty, narrow, and full of tide, never heard of that phrase. It was West standing up in the bow who spotted each unlighted channel marker, and guided them in safely. By dawn, the wind had moderated slightly, and everyone felt better. They went out and raised their spinnaker. West gazed up at the large billowing sail and said, "The spinnaker looks like a wind." He said, "Yeah, hey, we're hauling ass." There was something faintly ridiculous about his exclamations, but also something childlike that made his companion smile. He was grinning most of the day, a cockeyed little smile that collected in the corner of his mouth. When the captain remarked worriedly that his boat had never gone so fast before, West laughed. He made the sound mostly in his throat. It was a low and even noise, odd in itself and oddly provoked the kind of laughter that ghost stories inspire. It seemed to say, "Here's something that's not ordinary." A snapshot taken of the cockpit in the afternoon shows West sitting at the stern. Dark shadow of the day's growth of beard reveals that he passed adolescence some years ago, though just how many would be impossible to say. In fact, he is just 40. He wears glasses with flesh-colored rims and a heavier gray sweater that must have given him long faithful service hangs loosely on his frame. He looks as if he must smell of wool. He looks thin, with a long narrow face that a woman would be called horsey. A mane of brown hair swept back behind his ears, reached almost to his collar. His face is lifted, his lips pursed. He appears to be the person in command. One of the crew would remember being alone with him on watch one night. They were sailing under clear skies with a gentle breeze. Suddenly, at the slackening of the tide, the wind fell away, some clouds rolled in, and then just suddenly, when the tide began to run, the sky cleared up and the breeze returned. In a low and throaty voice, West made exclamations. "Did you see that?" He made his low and spooky laugh. His companion was about to say, "Well, I've seen this happen before." The tone of West's voice prevented him, however. He thought it would be rude to describe this event as ordinary. Besides, West was right, wasn't he? It was strange and wonderful the way the pieces of the weather sometimes played in concert. And in a way, it was fun to think that they had just encountered a natural mystery, and somewhat surprised at himself, West's companion suggested that even events like that made superstition seem respectable. West gave his little laugh, apparently signifying agreement. The psychologist, meanwhile, was waiting for West to go to sleep. He had not done so for more than a few hours altogether. By the third day, they were sailing in sunshine with a gentle breeze. The psychologist expected to see signs of exhaustion appear in West. Instead, West put on his bathing suit and took a long, vigorous swim beside the boat. Back at the restaurant near Portland, before they'd gone out into the storm, while they'd been sharing a meal that most of them soon regretted, West had told them, "I built computers." Although he spoke at some length about certain extraordinary-sounding new computing systems, the others came away uncertain about what role, if any, he had played in their construction. They felt only that whatever he did for a living, it was probably interesting and obviously important. One time while West was manning the tiller, the psychologist asked him how he had learned to sail. West didn't answer. A little later on, thinking he hadn't heard the question, the psychologist inquired again. "You already asked me that," West snapped. After a moment's silence, he wet his lips and explained that he had taught himself mostly as a boy. On another occasion, just to make conversation, one of the crew asked West what sort of computer he was building now. West made a face and looked away and muttered something about how that was work and this is his vacation, and he would rather not think about that. The people who shared the journey remembered West the following winter describing the nasty northeaster over dinner. The captain remarked, "That fellow West is a good man in a storm." The psychologist did not see West again, but remained curious about him. He didn't sleep for 4 whole nights, and if that trip had been his idea of vacation, where the psychologist wanted to know, did he work? In software, baby. Or hardware in this case. In tech. All right, how to make a lot of money. Okay. Okay. For a time after, what time is it? Okay. For a time after the first pieces of Route 495 were laid down across central Massachusetts in the middle of the 1960s, the main hazard to drivers was deer. About 15 years later, the traffic went. I remember reading Linus's book when I was a young lad. I couldn't have been more than 21 years old. Around that age. Let's see. I was probably 23, I think. 23 years old. I was reading Linus's book, and I was just so engrossed by it. I just absorbed every page. I could not put it down. This book, however, is not my style. I like the way Linus writes. Let's see. For a time after the first pieces of Route 495 were laid down across central Massachusetts, in the middle of the 1960s, the main hazard to drivers was deer. About 15 years later, although traffic went by in processions, stretches of the highway's banks still look lonesome. Driving down 495, you pass some modern buildings, but they quickly disappear, and then for a while there would be a little to see except the odd farmhouse and acres of trees. The highway traverses some of the ghost country of rural Massachusetts, like Troy. This region contains evidence of successful sackings in the pine and hardwood forests, which now comprise 2/3 of the state. Many cellar holes and overgrown stone walls that farmers left behind when they went west. Riverside textile mills, still the largest buildings in many little towns, but their windows not broken now, the machinery crumbling to rust, and the business gone to Asia and down south. However, on many of the roads that lead back behind the highway's scenery stand not woods and relics, but brand new neighborhoods, apartment houses, and shopping centers. Roads around them fill up with cars before 9 after 5. They're going to and from commercial buildings that wear on their doors and walls descriptions of new enterprise, digital equipment, Data General. They're at the edge of the woods. Those names seemed like prophecies to me before I realized that the new order they implied had arrived already. A few miles north of the junction of Route 495 and the Massachusetts Turnpike, off the access road, sits a 2-story brick building surrounded by parking lots. The sign warns against leaving a car there without authority. The building itself looks like a fort. It has a narrow window, an American flag on a pole out front, a dish antenna, and a lattice tower mounted on several corners of the roofs and slowly turning little TV cameras. This building, 14AB-14B, was fastened seamlessly to 14A. Some employees called the place Webo, but most referred to it as Westboro, after the name of the town inside whose borders the buildings happens to exist. Westboro is worldwide headquarters of Data General Corporation. Driving up to the building one day with one of the company's public relations men, I asked, "Who is the architect?" "We didn't have one," cried the beaming press agent. Company's engineers helped to design Westboro, and they made it functional and cheap. One contractor who did some work for Data General was quoted, unfortunately, as saying, "What they call tough auditing, we call thievery." However, they accomplished it. Westboro cost only about $19 a square foot, and at a time when the average commercial building in Massachusetts was going for something like $34 a foot. But looks do matter here. The company designed Westboro not just for the sake of thriftiness, but also to make plain to investors and financial analysts that Data General really is a thrifty outfit. There's no reason in our business to have an ostentatious display, a company analyst for investor relations explained. In fact, it's detrimental. The TV cameras on the roofs, the first defense against unscrupulous competitors and other sorts of spies and thieves, must comfort those who have a stake in what goes on inside. As for me, I imagine that somewhere in the building, men in uniforms were watching me arrive, and I felt discouraged from walking on the grass. The only door that opens for outsiders leads to the front lobby. The receptionist asks you to sign a logbook, which inquires if you are an American citizen, wants your license plate number, and so on. Still, you cannot pass the desk and enter the hallways beyond, not until the employee you want to see comes out and gives you an escort. When I inquired, the cheerful young receptionist said that once in a great while, some outsider would try to break the rules and try to slip inside. The lobby could belong to a motor inn. It has orange carpeting and some chairs, and a sofa upholstered in vinyl, on which salesmen and would-be employees languish, awaiting appointments. Now and then a visitor will stand and gaze into a plastic case. It contains a bare bones of the story that will feed the dreams of any ambitious businessman. The first Nova reads a legend on the case. Inside it sits a small computer about the size of a suitcase with a cathode ray tube, a thing like a television screen beside it. A swatch of prose on the back wall inside the case explains that this is the first computer that Data General ever sold, but the animal in there isn't stuffed. The computer is functioning, lights on, it softly blinks as it produces on the screen besides it a series of graphs, 10 years worth of annual reports, a précis of Data General's corporation's financial history. Left to their own devices, the engineers who work in the basement of building 14AB could surely have produced a flashier display, but a visitor from Wall Street who had never paid attention to this company before might have felt faint before the thing. The TV screen was blue, the graphs etched in white appeared in rotating sequence, and each one bore a name. Cumulative computers shipped since our founding started with 100 in 1969 and went right up to 70,700 in 1979. The image vanished. Net sales appeared to show that revenues had ascended without a hitch from nothing in 1968 to 507.5 million in 1979. That's net sales. That graph went away, and in its place came one describing profit margins. These hardly varied. The profits just rolled in year after year along a nearly straight line at about 20% before taxes of those burgeoning net sales. Someone accustomed to reading financial reports might have missed the full import of numbers on the screen, the glee and madness in them, but anyone could see that they started small and got big fast, monotonously. Mechanically, monotonously, the computer in the case was telling an old familiar story, the international materialistic fairy tale come true. Okay. The first modern computers arrived in the late 1940s, and although many more or less single-handed contributions fostered the technology, they did so mainly in the shade of a familiar association in America among the military, universities, and corporations. On the commercial side, IBM quickly established worldwide hegemony. It brought to computers the world's best sales force, all dressed in white shirts and blue suits. For some years, the computer industry consisted almost exclusively of IBM and several smaller companies. IBM and the Seven Dwarfs, business writers like to say. Then in the 1960s, IBM produced a family of new computers called the 360 line. It was a daring corporate undertaking. We're betting the company, one IBM executive remarked. Indeed, the project cost somewhat more than the development of the atom bomb. What the fuck? Really? Yeah. Not sure about that. But it paid off handsomely. It guaranteed for a long time the IBM's continued preeminence in the making of computers for profit. Meanwhile, though, new parts of the business were growing up and out from under IBM. My understanding is that the 360 was like a failure. I mean, not a complete failure, but like it wasn't like a huge success. Like they were like bogged down by a lot of like developmental issues. But I don't really know the history of the 360 in detail. In the early days, computers inspired widespread awe, and the popular press dubbed them giant brains. In fact, the computer's power resembled that of a bulldozer. It did not harness subtlety. though subtlety went into its design. It did mainly bookkeeping and math by rote procedures, and it did them far more quickly than they had ever been done before, but computers were relatively scarce. They were large and very expensive. Typically, one big machine served an entire organization. Often it lay behind a plate glass window, people with white gowns attending it, and those who wished to use it did so through intermediaries. Users were like supplicants. The process could be annoying. Scientists and engineers, it seems, were the first to express a desire for a relatively inexpensive computer that they could operate themselves. The result was a machine called a mini computer. In time, the demand for such a machine turned out to be enormous. Probably IBM could not have controlled this new market the way it did the one for larger computers. As it happens, IBM ignored it, and so the field was left open for aspiring entrepreneurs, often in the case young computer engineers who left corporate armies with dreams with dreams of building corporate armies of their own. For many years, sociologists and others have written of the computer revolution and impending or in progress. Some enthusiasts have declared that the small, inexpensive computer inaugurated a new phase of its upheaval, which would make computers instruments of egalitarianism. By the late 70s, practically every organization in America had come to rely upon computers, and ordinary citizens were buying them for their homes. Within some organizations, small bands of professionals had exercised absolute authority over computing, and the proliferation of small computers did weaken their positions. But in the main, computers altered techniques and not intentions, and in many cases served to increase the power of executives on top and to prop up venerable institutions. A more likely place to look for radical change was inside the industry actually producing computers. Generally, that industry grew very big and lively, largely because of a single invention. Shortly after World War II, decades of investigation into the internal workings of the solids yielded a new piece of electronic hardware called a transistor. I don't understand what that means. Shortly after World War II, the way this author writes is just very foreign to me. Shortly after maybe it's just because it's dated. Shortly after World War II, decades of investigation into the internal workings of the solids yielded a new piece of electronic hardware called a transistor. What is the solids? Inner workings of matter. And transistors don't really have, they're not atomic. I think that's what they're getting at here. Decades of investigation into the internal workings of the solids, which is matter, which implies subatomic stuff, which is obviously, Los Alamos, they were producing the atomic bomb. It's a lot of subatomic physics. But it yielded a new piece of electronic hardware called a transistor. I don't think the transistor has any relation to the development of nuclear weaponry. Does the development of the transistor have anything to do with the development, the R&D around the development of nuclear weaponry? William Shockley. Wartime mobilization of science. World War II fundamentally changed how science was done. Massive government funding. Okay, I could see how they can make that connection. It's not as literal as what I was thinking, but they're saying just the culture of research and funding research and development of like fundamental physics led to the development of the transistor. For its actual invention, 3 scientists at Bell Laboratories won the Nobel Prize. Transistors, a family of devices, alter and control the flow of electricity on circuits. One standard rough analogy compares their action of that to faucets controlling the flow of water in pipes. Other devices then in existence could do the same work, but transistors were superior. They are solid. They have no cogs or wheels, no separate pieces to be soldered together. It is as if the stones perform useful work. They are durable, take almost no time to start working, and don't consume much power. Moreover, as physicists and engineers discovered, they could be made very small, indeed microscopic, and they could be produced cheaply in large quantities. The second crucial stage in the development of the new electronics came when techniques were developed to hook many transistors together into complicated circuits into little packets called integrated circuits or chips. Imagine the wiring diagram of an office building inscribed on the nail of your little toe. The semiconductor industry, which is named for a class of solids out of which transistors are made, grew up around these devices and began producing chips in huge quantities. Chips made spaceships and pocket calculators possible. They became the basic building blocks of TVs, radios, stereos, watches, and they made computers ubiquitous and varied. They did not eliminate the sizable, expensive computer. They made it possible for the likes of IBM to produce machines of increased speed and capability, and still make handsome profits without raising prices much. At the same time, the development of chips fostered an immense and rapid growth of other kinds of computing machines. After mainframes, as the big computers were known, came the cheaper and less powerful mini computers. Then the semiconductor firms contributed the microprocessor, the essential work of a computer executed on a chip. For a while, the three classifications really did describe a company's product and define its markets, but then mainframers and microcomputer companies started making minis, and mini computer companies added micros and things that look like mainframes to the product lines. Meanwhile, a host of frankly imitative enterprises started making computers and gear for computers that could be plugged right into systems built around the wares of big successful companies. These outfits went by the names of plug compatibles and third-party peripheral manufacturers. Those who lost some business to them called them knockoff companies. Probably they helped maintain competition and prices. Many software houses sprang up to write programs that would make all those computers actually do work. Many customers, such as the Department of Defense, wanted to buy complete systems, all put together and ready to run with the turn of a key, hence the rise of companies known as original equipment manufacturers. So let me reread that. Many customers, such as the Department of Defense, wanted to buy complete systems, all put together and ready to run with the turn of a key, hence the rise of companies known as original equipment manufacturers or OEMs. They'd buy gear from various companies and put it together in packages. Some firms made computer systems for hospitals, some specialized in graphics, computers that draw pictures, and others worked on making robots. It became apparent that communications and computing served each other so intimately that they might actually become the same thing. IBM bought a share in a satellite, and that other nation state, AT&T, the phone company, started making machines that looked suspiciously like computers. Conglomerates, of which Exxon was only the largest, seemed determined to buy up every small computer firm they could. As for those observed the activity, they constituted an industry in themselves. Trade publications flourished. They bore names such as Datamation, Electronic News, Byte, Computer Mania. IBM, one executive of a mainframe company once said, represented not competition but the environment. and on Wall Street and elsewhere, some people made a business solely out of attempting to predict what the environment would do next. I once asked a press agent for a computer company what was the reason for all this enthusiasm. He held a hand before my face and rubbed his thumb against his fingers. Money, he whispered solemnly. There's so goddamn much money to be made. Examples of spectacular success abound. The industry saw some classic dirty deals and some notable failures too. RCA and Xerox lost about $1 billion apiece, and GE about $500 million making computers. It was a gold rush. IBM set up two main divisions, each one representing the other's main competition. Other companies did not have to invent competitors and did somewhat more of their contending externally. Some did, sometimes use illicit tools, carrying favor. What time was it? Okay. Carrying favor, seeking big orders for chips. Some salesmen of semiconductors, for instance, were known for whispering to one computer maker news about another computer maker's latest unannounced products. Firms fought over patents, marketing practices, employees, and once in a while someone would get caught stealing blueprints or other documents. And for these and other reasons, computer companies often went to court. IBM virtually resided there. Everyone sued IBM, it seemed. The biggest suit was Jarndyce versus Jarndyce of the industry. Involved the Justice Department's attempt to break up IBM. Virtually an entire large law firm was created to defend IBM in this case, which by 1980 had run 10 years and had been in continuous trial for several. Data General took its place in this bellicose land of opportunity in 1968 as a microcomputer company. By the end of 1978, this increasingly undescriptive term could, in some sense, be applied to about 50 companies. A principal, but by no means their only business, the manufacture and sale of small computers had grown spectacularly from about 150 million worth of shipments in 1968 to about 3.5 billion worth in 1978, and it would continue to grow. Most interested parties believed at the rate of about 30% a year. By 1978, Data General ranked third in sales of mini computers and stood among the powers in this segment of the industry. The leader was Digital Equipment Corporation, or DEC, as it is usually called. DEC produced some of the first mini computers back in the early 60s. Data General was the son, emphatically the son of DEC. A chapter of DEC's official history, the technical work that the company published, describes the making of a computer called the PDP-8. DEC sent this machine to market in 1965. It was a hit. It made DEC's first fortune. The PDP-8 says the official history established the concept of mini computers, leading the way to multi-billion-dollar industry. But the book doesn't say that Edison de Castro, then an engineer in his 20s, led the team that designed the PDP-8. Technical history mentions De Castro only once briefly and in another context. They expunged De Castro. In 1968, De Castro and two other young engineers succeeded from DEC. Several completely different versions of their flight exist and have now acquired the impenetrable quality of myth. Did they quit because, was this the unfaithful 8 or whatever? Was that DEC? Maybe it was DEC, I forget. No, it was, this is East Coast. The Traitorous 8 was West Coast with Stockley Semiconductor, I think it was. Several completely different versions of their fight exist and have by now acquired an impenetrable quality of myth. Did they quit because after long and heartful labor on a new design, they found that DEC's management would not build their new machine? DEC's management didn't turn down a new design of De Castro's, and afterwards, along with a man from another company named Herb Richmond, De Castro and two other engineers from Digital incorporated Data General and started building their own mini computer. But did they design this new machine after they succeeded, or had they done the job in secret using DEC's facilities while still on DEC's payroll? One version of the story suggests the latter. More than 10 years later, DEC's founder and president would tell reporters in Fortune that what they did was so bad we're still upset about it, but DEC never sued Data General founders, and clearly there were other reasons why Digital might have become upset. For within a year, DeCastro and company had set up shop in DC's own territory and had started racking in the loot. They rented space in what had been a beauty parlor in former mill town of Hudson, Massachusetts. Practically all that remains of that time is a black and white photograph of his first headquarters. In the foreground stand 4 young men with short hair wearing white shirts and skinny ties and sort of plain black shoes that J. Edgar Hoover men favored. The references are just so out of date for me. I just have no context to understand any of these references. They are engaged in what is obviously meant to look like routine conversation. The linoleum floor, the metal furniture evoke motor vehicle departments, and the youth in the picture could be members of some junior chamber of commerce playing capitalist for a day. Not shown in this bemusing picture is a shrewd and somewhat older lawyer from large New York firm who helped Data General's founders raise their capital and who became a crucial member of their team. What also doesn't show is the fact that some of these young men were already computer engineers of no mean repute. Their age, in this case, was no impediment, for computer engineers, like athletes, often blossom early. They started Data General at an auspicious time in the late 1960s, a period memorialized by John Brooks, the go-go years. Venture capital, among other things, abound. And although they started out with only $800,000 more lay in reserve, they also entered a good territory for fledglings. They could not have dreamed of moving in on IBM's market without truly vast amounts of capital. But the people who brought many computers, engineers, scientists, and mainly purchasing agents of OEMs understood the machines. A new manufacturer could reach them through relatively inexpensive ads and in trade journals, and didn't need to build a service organization right away. Since these customers could take care of themselves, these were all sorts of customers who could be expected to embrace the newcomer if the price was right. They prefer a bargain to a brand name. But around the time that when Data General established itself in the beauty parlor, other entrepreneurs were starting up mini computer companies at the rate about one every 3 days. Only a few of those other outfits survived the decade, whereas Data General, before it had exhausted its first and fairly modest dose of capital, achieved and never fell from that state of grace, a positive cash flow. Why? The company's first machine, the Nova, had a simple elegance about it that computer engineers I've talked to considered admirable for its time. It had features that DEC comparable offering didn't share, and it incorporated the latest, though not fully proven, advances in chip. Data General could build the Nova very cheaply. Such an important advantage can depend in computers on small things. In the case of the Nova, the especially large size of the printed circuit boards, the plates on which the chips are laid down, made a crucial difference for several reasons. Large boards tend to reduce the amount of hardware in a computer. Data General used boards much larger than the ones that DEC was using. Speaking of this difference and of other less important ones, one engineer remarked, the Nova was a triumph of packaging. Good machines don't guarantee success though, as RCA and Xerox and others have discovered. Herd Richard, who had helped to found Data General, said, "We did everything well, obviously. They did not manage every side of their business better than everyone else, but these young men, all equipped with large egos, and one who was around them at this time remarked, somehow managed to realize that they had to attend with equal care to all sides of their operation, to the selling of their machine as well as to its design, for instance. That may seem an elementary rule for making money in a business, but it is one that is easier to state than to obey. Some notion of how shrewd they could be is perhaps revealed in the fact that they never tried to hoard a majority of the stock, but use it instead as a tool for growth. Many young entrepreneurs confusing ownership with control can't bring themselves to do this. When they choose their lawyer who would deal with the financial community for them, they insisted that he invest some of his own money in their company. We don't want you running away if we get in trouble. We want you there protecting your own money. Richmond remembered saying such an agreement, though not illegal, might raise some eyebrows in some corners of the bar association. But the lawyer said, according to Richmond, that's the first time anyone made an intelligent proposition to me. Richmond also remembered that before they entered into negotiations over their second public offering of stock, after the company had been making money for a while and the stock they'd already issued had done very well indeed, their lawyer insisted that each of the founders sell some of their holdings in the company and each take down $1 million. This so that they could negotiate without the dread of losing everything. Having to go back to your father's gas station, Richmond called that nightmare. As for the name of the theory behind selling enough stock to become millionaires, Richard told me, I don't know how you put it in the vernacular. We called it the fuck you theory. In the computer business, your market can be your fate. Although by the late 1970s, it was hard to define a company's place in the industry by the sorts of machines that it had made. Certain broad historical distinctions in the way of doing business still divide a large part of the industry into three segments. Differences showed up in the nature of the company's expenditures. IBM and other mainframe companies spent more time selling their products and serving their customers than they did in actually building their machines. They sold their computers to people who were actually going to use them, not to middlemen, and this market required good manners. Microcomputer companies sold equipment as if it were corn in large quantities. They spent most of their money making things and competed not by being polite, but by being aggressive. Many computer companies split the differences more or less. They sold some machines and services to actual users, but spent most of their money on hardware and did a big business by selling machines in quantity to OEMs. From these distinctions, others hung. A seasoned executive in marketing explained, with micros, it's even more competitive, but historically, the world of mini computers is very rough and tumble. IBM would say, you got a problem, Mr. Customer? A team of 4 will be there in an hour. Implicitly, a data general would say to its customers, you have to look out for yourselves. The sophisticated customer, particularly the OEM who buys a lot of computers and looks for discounts, not services, goes for minis. They're capable of living in a rough and tumble world, and I'm not sure that IBM with this organization can compete with the traditional mini computer market. It's like putting a goldfish in a bowl with a piranha. So you could say that Data General entered a territory that asked for certain brashness, and you could also say that the life in this territory became less decorous than it had been when Data General came along. They set out to get noticed, first of all. In the lobby at Westboro hangs a copy of the first advertisement Data General ever ran. It consists of just one page. On one side of the page is a grainy photograph of a man's face. This person looks about to do something very mean. On the other side of the ad, he speaks, I am Ed DeCastro, president of Data General Corporation. 7 months ago, we started the richest small computer company in history. This month, we're announcing our first product, the best small computer in the world. The message goes on for a while and winds up as follows. Because if you're going to make a small, inexpensive computer, you have to sell a lot of them to make a lot of money, and we intend to make a lot of money. This ad's chief architect, a man named Alan Cluchman, who was the company's first director of marketing, told me with a smile that ad was independent of any aspect of Mr. Del Castro's personality that I knew about at the time. He's the shyest guy I know. He's essentially a pretty humble private guy. The ad achieved a certain local fame. It said what many others presumably were thinking, but that what none of them felt they should say publicly. For some years thereafter, most of Data General's advertisements contained something slightly brazen. One of the best-known ads was published Some people in the company were by then apparently having second thoughts about the firm's image, but the copy of this unpublished ad hangs in Del Castro's office over the Data General logo on a field of white and blue. It reads, "They say IBM's entry into mini computers will legitimize the market. The bastards say welcome." That was it. 15 minutes. Before Data General revealed the Nova in 1969 at the industry's yearly fair, the National Computer Conference, the marketer Clutchman talked a trade magazine into putting a picture of the Nova on its cover. They rented billboards on the road from the airport to the conference and put a picture of the Nova on them. At a hotel where most of the people attending the conference stayed, they had management into the hall. They talked the management into having the bellboys distribute free copies of the Wall Street Journal with Data General's advertising flyer inside. At the show itself, they raised the other placard bearing their company's name higher than any other. When it came to pricing their machine, they announced extraordinary discounts for customers who bought machines in quantity. Never mind that customers had to buy a virtual warehouse of Novas to get a truly big discount. Data General had brought a new ferocity, a bit of 42nd Street, to the pricing of mini computers. DEC owned 85% of the business, and there was no strong number two. We had to distinguish ourselves from DEC, Klutchman remembered. DEC was known as a bland entity. Data General was going to be unbland, aggressive, hustling, offering you more for your money. We spread the idea that Data General's salesmen were more aggressive than DEC's, and they were because ours worked on commissions and theirs worked on salaries, but I exaggerated the aggressiveness. According to Klutchman, DEC actually gave them some help in setting up the Hertz-Avis thing. DEC's management, he said, ordered their salesmen to warn their customers about Data General. It was great because their customers hadn't heard about us. Klutchman, imagine DEC's salesman telling DEC customers that a dangerous new company was on the prowl, and DEC's customers responding to this news by saying, "Where is this Data General so we can be sure to avoid them? What's Data General's phone number so we'll be sure not to call it?" Klutchman laughed. The calls just rolled in. DEC's customers would say, "We hear you're bad guys. You must be doing something we ought to know about." And thinking back to those first heady days, when nearly every little strategy seemed to pay off, the first millions started coming in. Klutchman said it was probably more fun than I or anyone else has ever had in business. It was great ego satisfaction. It was just pure gas. At the end of fiscal 1978, after just 10 years of existence, Data General name appeared on a list of the nation's 500 largest industrial corporations. In that band of giants known as the Fortune 500, it stood in 500th place in total revenues, but much higher in respect to various indices of profit, and for a while climbed steadily higher on the list. Surely by 1980, such a record entitled Data General to respectable Surely by 1980, such a record entitled Data General to respectability. But some trade journalists still looked askance. This book has introduced me to a lot of new words just in the first chapter. Askance. But some trade journalists still looked askance at the company. Once told me Data General was widely known among his colleagues as the Darth Vader of the computer industry. Investors still seemed jittery about Data General stock. An article published in Fortune in 1979 had labeled Data General the upstarts, while calling DC the gentleman. The memory of that article, particularly the part that made it sound as if Data General routinely cheated its customers, still rankled. Herb Richmond. Building 14AB is essentially divided into upstairs and a downstairs, and in one corner of the upstairs, the corporate officers reside. There is no mahogany here. There is no ostentation in the boss's quarters. it is ostentation in reverse. The table in their conference room, it was proudly said, was the same that they had used when the company was small. Richmond's office was comparatively plush, but saying, "We consider ourselves the Robert Hall of the computer industry." Richmond pointed out that he had paid for all the furnishing himself, and what looked like paneling on his walls was really just wallpaper. Among the founders of the company, only De Castro, the much talked about president, and Richmond remained engaged in daily operations. Richmond had come up through the industry in sales and super salesman, some call him, and he had created and run Data General's sales force, which was known, if not notorious, for its aggressiveness. Curly hair, trim, in his 40s, Richmond wore a nicely tailored denim jacket and no tie. "I'm one of the few guys that money made a nice guy out of," he said. "Before I was just driven, clawing. Success has made me more rational and introspective." He remarked that not long ago he had been playing tennis with a man who had seemed to him just an ordinary fellow, but then he had found out the man was actually president of an oil company, and it was one of the largest oil companies in the world. "I was just in awe of him," said Richmond. He added softly, "And yet I bet my net worth greatly exceeded his." The stock that Richmond himself owned at Data General was worth about $13 million then, but he seemed to say he was unhappy with the way certain organs of the press depicted his company's achievements. They were, Richmond believed, too often depicted as ruffians, not as merely rough, which they were proud to be. "We agree that a lot of things we've done around here are wild," he said, "but we can understand why they were tabloid instead of the but we can't understand why we're tabloid instead of the New York Times." Some part of Data General's reputation was easy to explain. The company had produced it themselves, and maybe it had gotten a little out of hand. Richmond suggested, "We've done so much so well for so long that everyone seems to think we have to be doing something illegal." A good point, but not a full accounting. Some years back, in the early 70s, a company called concurrency accused Data General's officers of arranging the burning of a factory. Concurrency had been making computers that performed almost identically to Data General's machines. The theory was that Data General had taken a shortcut in attempting to get rid of this competitor. In time, the courts found no basis for those charges and dismissed them. Indeed, it seemed preposterous to think that the suddenly wealthy executive of Data General would risk everything, including jail, to resort to arson just to drive away what was, after all, a small competitor. But Wall Street didn't see it that way, apparently. When Concurrency made its accusation, Data General's stock plummeted. There was such a rush to unload it that the New York Exchange had to suspend trading of it for a while. More peculiar was the fact that many years later, some veteran employees far down in the hierarchy would say privately that they believed someone connected with the company had something to do with that fire. Not the officers, but some renegade within the organization. They had no basis for saying so, no piece of long hidden evidence. It seemed to me as if it was something that they wanted to believe. Okay. Well, we're almost done here. I'll just finish this up. "I got this feeling more and more turning down the road at Building 14AB. One day, a veteran engineer pointed out the sign that warned against unauthorized parking. 'The first sign you see says don't,' he remarked. He imagined another sign by the road that would say, 'Use of excessive force has been approved.'" The engineer laughed at the thought. In a land of tough and ready companies, there's some of Data Engineer's employees seem to want to think was the toughest and the readiest around. Certainly, Data General's reputation had other underpinnings beside advertisement and imitation. An industry where sharp marketing practices were common, Data Generals were as sharp as any, and by the late 1970s, competitors were challenging some of them to federal court. To the contention leveled in Fortune that Data General played especially rough with its customers, it was only fair to add that many Data General's customers knew very well what sort of market they were in, and moreover, it was clear that the company could not have survived if most of its customers had not felt at least fairly satisfied. But Data General was litigious towards customers as well as others. "Sure," said Richmond, "if people don't pay us are breach of contract, we litigate them. They did so at least in part to assure Wall Street that they weren't the sort of company that would accumulate a crippling number of bad debts. The salient feature of Data General, however, what that sharp-eyed, astonished visitor from Wall Street would have pondered was its growth. This was indeed the industry's salient characteristic. In the main computer companies that were not dying were growing. They had to do so just to stay alive, it seemed. But no company whose primary business was making computers had grown more rapidly than Data General. Bursts of growth were not uncommon, but Data General had been bursting for a decade. And what's more, it had been maintaining the highest profit margins in the industry next to IBM's. All this would have impressed analysts from Wall Street, of course, but would also have given him pause. The interesting is they're supposed to be like competing on cost, and they still have very high margins. That's interesting. Usually, high margin, you're not competing on cost. Building 14AB is its sparse furnishings. The facts that Data General paid its stockholders no dividends, and that its top managers dispensed to themselves and other officers extraordinary small salaries, betting out rewards in the form of stock instead, all were signs of a common purpose. The company had displayed extravagance when it came to financing its tendency to go to court. Otherwise, the management seemed bent on saving all their cash to feed the hungry beast of growth. And of course, the more the beast gets fed, the bigger it becomes, the more it wants to eat. It is one thing for a company with revenues of $1 million a year to grow 30 or 40% in a year, and quite another for a $500 million company to pull off the same trick. Analysts on Wall Street sometimes become boosters of the companies they follow, looking for an opinion that was certain to be disinterested. I asked an old friend, a veteran analyst of securities, to take a look at Data General's numbers. He had an advantage of never having followed the company before, and in return for anonymity, he agreed to my proposal. A couple weeks later, he called me back. It seemed to him that Data General was bent on continuing to grow at 30 to 40% a year. He pointed out that this meant large growth in everything, in the need for capital, new buildings, new employees. Between 1974 and 1978, for instance, Data General had hired about 7,000 new employees. God damn, that's a lot. Roughly tripling its numbers. In 1 year alone, the company had increased its ranks by 71%. They didn't just imagine the difficulties of finding that many qualified people so quickly, and what must it be like, he asked, to work at a place like that. You'd come to work some morning and suddenly find yourself in charge of a dozen new people, or suddenly beneath a new boss to whom you would have to prove yourself all over again. That sort of growth puts a strain on everything, analysts concluded. It's going to be intriguing to see if they get caught. He thanked me for putting him onto such a marvelous entertainment. Where did the risks lie? Where could a company go badly wrong? In many cases, a small and daily growing computer company did not fall on hard times because people suddenly stopped wanting to buy its products. On the contrary, a company was more likely to asphyxiate on its own success. Demand for its products would be soaring, and the owners would be drawing up optimistic 5-year plans when all of a sudden something would go wrong with their system of production. They wouldn't be able to produce the machines that they had promised to deliver. Lawsuits might follow. At the least, expensive parts would sit in inventory. Revenues would fall. Customers would go elsewhere or out of business themselves. Data General got one leg caught in this trap back in around 1973. 6 years later, a middle-level executive sitting in an office upstairs at headquarters remembered that time. We were missing our commitments to customers. We just grossly fucked over our customers. We actually put some entrepreneurs out of business, and I think some of them may have lost their houses, but we recovered from our shipment problems and never repeated them. Another way of fouling up had less to do with the company's own growth than with the growth occurring all around it. From observers of the industry came such comments as, things change fast in the computer business. A year is a hell of a long time. It's like a year in a dog's life. In every segment of the industry, companies announce small new products for sale every day. Companies brought out new lines of computers, much more powerful than the ones they had replaced only every few years or so. But considering all the work that went into them and the fact that they required a redirection of effort throughout the company, the pace at which these major announcements came was very rapid too. Conventional wisdom held that if a company fell very far behind its competitors in producing the latest sorts of machines, it would have a hard time catching up. A failure to stay abreast could have serious consequences because major new companies played crucial roles in other businesses of the companies. In the other businesses of the companies, they helped them sell all their little products and often their older types of machines. At some companies, the task of guarding against this sort of crisis fell mainly to engineers working below decks, as it were. Executives might make the final decisions about what would be produced, but engineers would provide most of the ideas for new products. After all, engineers were the people who really knew the state of the art and who were therefore best equipped to prophesy changes in it. At Data General, an engineer could play such an important role. It was there for the taking. The President de Castro liked self-starters. It was said initiative was welcome at Data General, and in the late 70s it appeared that just finish up the chapter here. Initiative was welcomed at Data General, and in the late 70s it appeared that the company had need for some initiative from its engineers, for Data General was in a bind. The firm had fallen behind the competition. It hadn't yet produced the latest big thing in mini computers. Early in 1979, the businessman who told me about Data General's problems and recovery back in 73 hit upon a heroic metaphor for success in the computer business. The major thing, he said, is avoiding the big mistake. It's like downhill ski racing. Can you stay right on that edge beside disaster? At Data General, we keep coming up with things that are basically acts of recovery. What Tom West and his people are doing is a great act of recovery. So Tom West is the guy at Data General, I guess, and he's the captain too. Cool. All right, well, that's chapter 2, The Wars. I'm gonna leave it there. This is a nice little book to read when I don't really want to learn more about x86-64 assembly. Yeah. I mean, it's how many pages here? Just a couple hundred pages. And I read 30 pages, so I could read this in 10 nights. Or even less. Cool. All right. I'm going to sign off then. I saw someone message me. I think that might be a spammer. Cool. So I have gym in the morning, and then I have this APOD meeting after gym and all my morning stuff. So I won't be getting on until 10:30 tomorrow morning. So not a lot of time to stream tomorrow, but I will be on, and we'll pick up on the optimization stuff. Where do we leave off here? Enhancing instruction level and parallelism. So that should be fun. And then that gets into SIMD. We could do a SIMD website. That'd be really fun to dive into. Yeah, cool. All right, I'll go ahead and sign off there then. Later.